Deep beneath the French-Swiss border, the Large Hadron Collider accelerates protons to near light speed and smashes them together, recreating the universe's earliest moments. From these collisions emerges the top quark, the heaviest particle ever discovered, more massive than a gold atom, yet smaller than a proton. The top quark exists for only a trillionth of a second, decaying before it can form composite particles. This fleeting existence lets us study its pure properties, offering a rare glimpse into the quantum world and the universe's deepest mysteries. Quantum entanglement links two particles so that measuring one instantly reveals the state of the other, no matter the distance. At CERN's ATLAS experiment, scientists measured this with top quarks and anti-top quarks, created with opposite spins, like quantum coins, always perfectly correlated. Their spins act as quantum bits, or qubits, the building blocks of quantum computers. This discovery marks just the beginning of a new journey into the quantum world, towards something even more mysterious: magic. Not all entanglement is created equal. Some entangled states, known as stabilizer states, are surprisingly simple. Although they seem strange to us, they can be simulated quite efficiently on a classical computer. They follow predictable rules. But there is another, more powerful class of quantum state. Physicists with a wonderful sense of flair call these magic states. A magic state is a special kind of entanglement, one so complex and rich that a normal computer would choke trying to simulate it. It is this magic that is believed to be the essential fuel for a quantum computer to achieve its incredible potential. The difference lies in a deep quantum property called contextuality. It means the result of a measurement depends on what else you are measuring at the same time. It's a hallmark of true quantum weirdness. Magic states have this property in spades, which is what makes them so powerful and so difficult to replicate classically. In late 2024, following a brilliant theoretical proposal, the CMS experiment at CERN set out to find this magic. They analysed their top quark data in a new way, looking not just for the correlation of entanglement, but for the signature of this deeper complexity. And they found it. In the spring of 2024, they announced the first observation of magic in a system of elementary particles. This was a landmark moment, connecting the world of high-energy physics with the frontier of quantum computing. It confirmed that nature, in its most extreme moments, doesn't just produce simple entanglement. It produces the high-octane, complex quantum states needed to unlock computational power far beyond our current reach. It's as if we found that lightning strikes don't just produce light, but they forge the very ingredient needed for a future technology. This sensitive hunt for quantum correlations led to another surprise. Scientists noticed some particle pairs were extra entangled, their connection stronger than predicted. This subtle sign pointed to something long theorized but never seen: Toponium. This is an exotic, ultra-short-lived atom made of a top quark and an anti-top quark orbiting each other before they annihilate. Its discovery, a byproduct of the search for magic, shows how looking at the universe in a new way can lead to unexpected treasures. The universe, it seems, is always ready to surprise us. At the edge of reality, new discoveries let us explore the biggest questions in science. How does the fuzzy world of quantum mechanics become the solid reality we know? The top quark's decay lets us watch this transition in real time. Some physicists now wonder if time itself is an emergent property of quantum entanglement. Using the universe's heaviest particles, we're probing the most fundamental connections of reality. The only certainty is that by smashing particles together, we'll keep asking bigger, bolder questions about our magnificent cosmos.